In this video, I'll introduce some of the basics associated with circuits that contain energy storage elements. This will include a discussion of some of the signals that are commonly encountered in the analysis of systems with energy storage. Before I start talking about systems that store energy, let's revisit an example of a system that doesn't store energy. This circuit is an inverting voltage amplifier. For this circuit, the output voltage is equal to the negative of the input voltage times the ratio of these two resistances. With these resistors, the output voltage is equal to the negative of 5 times this input voltage. With this source and switch, the input voltage is 0 for time less than 0 and 2 volts for time greater than 0. Graphically, the input voltage looks like this. Since the output voltage is just negative 5 times this input voltage, the output voltage looks like this. Notice that the output voltage at any time depends only on the input voltage at that same time. This system doesn't remember what happened before. The output can instantaneously respond to any change in the input. Dynamic systems are systems that have energy storage elements. We've already seen that energy can't change instantly. So in some sense, the energy storage elements have a memory of what's happened already. This means that the output waveform may depend on previous values of both the output and the input waveforms. So we have to define both the inputs and the outputs as functions of time. The input and output functions can have different shapes if we represent them graphically. A familiar example of this is a mass that's sliding on a surface with some friction. Suppose that there's a constant force applied to the mass for a long time and then removed suddenly, as shown here. In this case, the velocity of the mass will be a constant value before the force is removed. After the force is removed, the mass will gradually slow down until it comes to rest. This situation is analogous to driving a car at a constant speed and then taking your foot off the accelerator. The shapes of the input and output waveforms are not the same, and the output waveform reflects the fact that the energy in the system can't change instantaneously when the input force changes. The outcome of this is that the inputs and outputs of a dynamic system have to be characterized as functions of time. This is a significant change in our mindset, since the response of systems without energy storage didn't require us to treat the signals as functions of time. The output was always just dependent on the input value at that same time. Since the input and the output signals must now be treated as functions of time, the rest of this video will be spent defining a couple of types of time-varying signals that we'll be using in the near future. For now, we'll work with only two types of time-varying signals: step functions and exponential functions. The reason for this is that at first, we'll only be interested in the responses of linear systems that are governed by ordinary differential equations with constant inputs. Constant values, which will model our inputs, are conveniently represented as step functions. The responses of linear systems are generally described in terms of exponential functions. So for this category of problems, we'll need to use these types of functions. First, I'll talk about step functions. Step functions are commonly used to represent functions that consist of constant values, although these values can change instantaneously from one level to another. Step functions are represented in terms of what is called a unit step function, which I'll represent as u sub 0 of t. u0 of t is defined as being 0 for time less than 0 and 1 for time greater than 0. For the purposes of this course, we don't need to define a value for the step function at time t equals 0. Graphically, the unit step function looks like this. I can physically generate a unit step function with a 1-volt source and a switch that closes at time t equals 0, as shown here. The voltage at these terminals changes from 0 to 1 volt instantaneously at time t equals 0. Unit step functions can be scaled and shifted to generate other similar functions. Scaling just consists of multiplying the unit step function by a constant. If I multiply the unit step function by k, the resulting function is 0 for t less than 0 and k for t greater than 0. Graphically, the function looks like this. It shifts from a value of 0 to a value of k at time t equals 0. Step functions can also be shifted or translated in time by changing the argument of the function. A step function, u0 of t minus a, shifts the unit step function to the right along the time axis by a distance a. Remember that the unit step function changes from 0 to 1 when the argument's 0. In this case, the argument is 0 when time is equal to a. Graphically, the function looks like this. The unit step function can be shifted to the left by adding a positive value a rather than subtracting the value from the argument. As an example of using step function to model a physical system, we have a 6-volt source in series with a switch. The switch closes at time t equals 1 second and opens up again at time t equals 3 seconds. We want to use step functions to model the voltage across these terminals. This is a graphical representation of this voltage V of t. The voltage is 0 volts before t equals 1 second, 6 volts between t equals 1 and t equals 3, and then 0 volts again after t equals 3 seconds. I can use a step function that's been shifted and scaled to model the change from 0 to 6 volts. This step function is 6 times u0 of t minus 1. Now I need to remove this value of 6 for t greater than 3. I can add a negative step function that goes to negative 6 volts, and this will be negative 6 times u0 of t minus 3. Superimposing these two gives me the final function, which is 6u0 of t minus 1 minus 6u0 of t minus 3. Exponential functions are extremely important in the modeling of linear systems. The form that I'll use to represent exponential functions is f of t is equal to some number a times e to the minus t over tau. E is just a constant value, approximately 2.718. Tau is called the time constant of the system. It provides a rate at which the exponential decays. For us, the time constant will always be a positive number. Graphically, the exponential function looks like this. It increases exponentially as time goes to negative infinity and decreases exponentially to 0 as time goes to positive infinity. In this class, I'll usually define exponential functions for time greater than or equal to 0 and set the value of the function to 0 for times less than 0. This function can also be represented in terms of the unit step function. The appropriate function is f of t is equal to a times e to the minus t over tau times u0 of t. The u0 multiplies the exponential by 0 for time less than 0 and by 1 for time greater than 0. So the desired behavior is recovered without having to define a piecewise function. A plot of this function is shown here for t greater than 0. The value of the function at time t equals 0 is a, since the function is a times e to the 0th power, which is just a. The function goes to 0 as time goes to infinity, since e to the negative infinity is 0. The time constant is the time at which the value of the function is 0.368 times its original value. When t is equal to tau, e to the minus t over tau equals e to the negative 1, which is 0.368. After another time constant, the function will be 0.368 squared times its original value, since this term becomes e to the minus 2, or 0.368 squared. Another way to state this is that the value of the function decreases by 63.2% every tau seconds. Finally, let's take a look at the effect of varying the time constant. As the time constant increases, the time required for the function to decay also increases. If the time constant goes to infinity, the function takes an infinite amount of time to decay and the exponential function becomes a step function. So far, I've introduced the voltage-current relationships for electrical energy storage elements and the types of functions that commonly occur when constant inputs are applied to systems with energy storage elements. Next, I'll write and solve the equations governing these types of systems.